Hello and welcome to AraaTech, especially those who are data lovers. Today we are presenting World of Data Science, where raw information transforms into meaningful insights. Whether you are a seasoned professional looking to sharpen your skills or a curious newcomer eager to explore the possibilities, you are in the right place. Data science is the art of extracting knowledge from data. And in the next few minutes, we will start a crash course that demystifies the key concepts, tools, and techniques that make data science a powerful force in today's digital landscape. Buckle up as we unravel the secrets behind data wrangling, machine learning, and the fascinating journey from raw numbers to actionable intelligence. Let's begin this exhilarating crash course together and unlock the doors to the captivating world of data science. Please don't forget to subscribe, like, and share. Thank you very much. Let's start our journey. Data science. Data science is a multidisciplinary field that involves extracting insights and knowledge from data through various methods, including statistical analysis, machine learning, and data visualization, to inform decision making and solve complex problems. Statistics. Descriptive statistics definition. Descriptive statistics involve methods for summarizing and describing the main features of a dataset. These features include measures of central tendency, mean, median, mode, and measures of dispersion, range, variance, standard deviation. Importance. Descriptive statistics provide a concise overview of the dataset, helping to identify patterns, trends, and the distribution of values. Inferential statistics definition. Inferential statistics are techniques used to make inferences or predictions about a population based on a sample of data. This includes hypothesis testing and confidence intervals. Importance. Inferential statistics allow data scientists to draw conclusions beyond the observed data, making generalization about populations. Probability definition. Probability is a measure of the likelihood that a particular event will occur. In data science, it's crucial for understanding uncertainty and randomness. Importance. Probability theory informs the basis for many statistical methods, especially in inferential statistics. It helps quantify uncertainty in prediction and decisions. Sampling techniques definition. Sampling involves selecting a subset of data from a larger population. Different sampling techniques such as random sampling or stratified sampling ensure the sample is representative. Importance. Proper sampling is essential for generalizing insights from a sample to the entire population, maintaining the integrity of statistical analysis. Central limit theorem definition. The central limit theorem states that for a large enough sample size, the distribution of the sample mean will be approximately normally distributed, regardless of the shape of the population distribution. Importance. It's a fundamental concept in inferential statistics, enabling the use of normal distribution properties in hypothesis testing and confidence intervals. Correlation and causation definition. Correlation measures the statistical association between two variables, while causation implies a cause and effect relationship between them. Importance. Understanding the difference between correlation and causation is crucial for making informed decisions based on data, as correlation does not imply causation. Regression and analysis definition. Regression analysis models the relationship between a dependent variable and one or more independent variables. It helps predict the value of the dependent variable based on the values of the independent variables. Importance. Regression is used for making predictions and understanding the strength and nature of relationships between variables. Statistical significance. Definition. Statistical significance indicates whether an observed effect or relationship in data is likely to be genuine or if it could have occurred by chance. Importance. Determining statistical significance is crucial in hypothesis testing to draw valid conclusions from data. Outliers. Definition. Outliers are data points that deviate significantly from the rest of the data. They can affect the accuracy of statistical analysis. Importance. Identifying and handling outliers is important for maintaining the integrity of statistical analysis and ensuring robust results. Confidence intervals. Definition. A confidence interval provides a range of values within which we can reasonably expect the true population parameter to lie. Programming. Definition. Programming is the process of creating a set of instructions that tell a computer how to perform a task. These instructions are written in a programming language which serves as a bridge between human understanding and the computer's processing capabilities. Importance. Programming is the fundamental skill that enables humans to communicate with computers and create software. It allows us to automate tasks, build applications, and solve problems by providing step-by-step instructions to a computer. Programming. Key concepts. Syntax. Definition. Syntax refers to the set of rules that dictate how programs written in a programming language should be structured. It's like the grammar of the programming language. Example. In English, proper syntax might be I like pizza, whereas incorrect syntax would be I pizza like. Variable definition. Variables are containers for strong data values. They have names and can hold different types of information such as numbers or text. Example. If you want to store the age of a person, you could use a variable like age and assign it a specific value. Control flow definition. Control flow refers to the order in which instructions in a program are executed. It involves decision-making, if statement, and repetition loops. Example. If it's raining, take an umbrella. Decision-making. Repeat a task until a condition is met. Repetition. Functions. Definition. Functions are blocks of code that perform a specific task. They allow for code reuse and organization. Example. In a recipe, a function might be mix ingredients or bake cake, each serving a specific purpose. Data structures. Definition. Data structures are ways of organizing and storing data for efficient manipulation. Common types include lists, arrays, and dictionaries. Example. In a grocery list, items can be organized in a specific order, list, or categorized by type, dictionary. Loops. Definition. Loops enable the repetition of a set of instructions until a certain condition is met. They help automate tasks. Example. Repeatedly checking your email until there are no unread messages, looping. Conditional statement. Definition. Conditional statements allow the program to make decisions based on certain conditions. They control the flow of the program. Example. If it's sunny, go for a walk. Otherwise, stay indoors. Conditional decision. Comments. Definition. Comments are non-executable lines in code used for human-readable explanations. They don't affect the program's functionality. Example. In a recipe, a comment might explain why a certain step is crucial. Input and output definition. Input involves receiving data while output is the result of processing that data. These operations enable interaction with the user. Example, a calculator program takes numerical input and produces the result as output. Debugging definition. Debugging is the process of finding and fixing errors or bugs in the program. Example, if a recipe does not turn out as expected, reviewing each step to identify and correct mistakes, debugging. Understanding programming concepts is like learning a new language. Once you grasp the basics, you can express yourself and solve various problems through code, just as you won't expect to become fluent in a language overnight. Programming is a skill that develops with practice and experience. Data cleaning and pre-processing definition. Data cleaning and pre-processing involve the tasks of identifying and correcting errors, handling missing information, and organizing raw data into a format suitable for analysis. It's like preparing ingredients before cooking, ensuring everything is in the right order and condition. Importance. Clean and well-organized data is crucial for accurate analysis and model building. Data cleaning ensures that the data is reliable, consistent, and ready for meaningful insights. Key concepts. Handling missing values. Explanation. Missing values in a dataset can occur when information is not recorded. Dealing with missing data involves strategies like removing rows with missing values or filling them with appropriate substitutes. Example, in a survey, if some participants did not answer a question, you might decide to either exclude those responses or estimate the missing values based on other information. Removing duplicates. Explanation. Duplicate entries can distort analysis. Identifying and removing duplicate records ensures that each data point is unique. Example, if a list of customer orders has the same order repeated, removing duplicates ensures accurate order count. Handling outliers. Explanation. Outliers are extreme values that deviate significantly from the majority. Addressing outliers involves deciding whether to keep, modify, or remove them based on the context. Example, in a dataset of student exam scores, an outlier might be a score much higher or lower than the usual range. Normalization and scaling. Explanation. Normalization and scaling are techniques to bring numerical features to a standard range. This ensures that no single feature dominates the others. Example, scaling could be like converting temperatures from Celsius to Fahrenheit for consistency. Encoding categorical variables. Explanation. Categorical variables represent categories, that is colors, gender, and need to be encoded into numerical values for analysis. Example, converting red, blue, and green to 1, 2, and 3 respectively for easier computation. Data imputation. Explanation. Data imputation involves filling in missing values using statistical methods or estimates. It helps maintain the integrity of the dataset. Example, if the temperature was not recorded at a specific time, imputation might involve using the average temperature for that time of day. Handling inconsistent data. Explanation. Inconsistent data may arise from typos, errors, or variations in recording. Standardizing formats and correcting errors ensure consistency. Example, standardizing date formats, that is month, day, year, to avoid variations, that is day, month, year. Feature engineering. Explanation. Feature engineering involves creating new features from existing ones to enhance the model's performance. Example, combining height and weight to create a new feature, body mass index, BMI. Dealing with skewed data. Explanation. Skewed data, where values are reconcentrated in one range can impact analysis. Techniques like log transformation help mitigate skewness. Example, in income data, most people might have average incomes, but a few with extremely high incomes can skew the distribution. Handling time and date data. Explanation. Time and date data may require special handling. Extracting meaningful features, day of the week, month, can aid analysis. Example. Analyzing sales data may involve extracting the day of the week to identify peak sales days. Data cleaning and pre-processing are akin to preparing a canvas for painting. Ensuring that the canvas is clean and ready allows the artist to create a masterpiece. Similarly, clean and well-prepared data sets the stage for meaningful insights and accurate analysis in the realm of data science. Data exploration. Definition. Data exploration is the process of visually and analytically examining a dataset to understand its characteristics, patterns, and distributions. It's like exploring a map before a journey, helping you grasp the landscape before making decisions. Importance. Data exploration is crucial for gaining insights into the structure and content of a dataset. It aids in identifying trends, outliers, and potential areas of interest, setting the foundation for further analysis. Key concepts. Summary statistics. Explanation. Summary statistics provide an overview of key properties of the dataset, such as mean, median, and mode for numerical features. Example, calculating the average height of a group of people or the most frequently occurring value in a set of numbers. Distribution, visualization. Explanation. Visualizing the distribution of a data helps understand how values are spread across different ranges. Example, using a histogram to see how grades are distributed in a class, whether most students scored high, low, or somewhere in the middle. Correlation analysis. Explanation. Correlation analysis examines the relationship between pairs of variables. Positive correlation means they move together. Negative correlation means they move opposite each other. Example, observing if there is a correlation between studying hours and exam scores. Scatter plots. Explanation. Scatter plots display individual data points in a two-dimensional space, helping identify relationships between variables. Example, plotting data points for heights and weights to see if there is a trend or pattern. Box plots. Explanation. Box plots show the distribution of a dataset and highlight potential outliers. They are useful for understanding the spread and central tendency. Example, using a box plot to visualize the salary distribution in a company and identify any unusually high or low salaries. Frequency tables. Explanation. Frequency tables display the count of occurrences of different values in a dataset. Example, creating a frequency table for eye colors in a group of people. Data distribution shapes. Explanation. Identifying the shape of data distributions, normal, skewed, bimodal, provides insights into the nature of the data. Example, recognizing whether a set of test scores forms a bell curve or has an asymmetric shape. Data grouping. Explanation. Grouping data based on specific criteria helps understand patterns within subgroups. Example, grouping sales data by region to analyze regional performance. Feature relationships. Explanation. Examining how different features interact or relate to each other can reveal important patterns. Example, exploring how temperature and ice cream sales are related during different seasons. Data spread and range. Explanation. Analyzing the spread and range of data points helps gauge variability. Example, understanding the range of ages in a population to see how diverse or concentrated the age distribution is. Data exploration is akin to wandering through a garden, observing the variety of flowers and understanding their colors and shapes. It's a crucial step in the data science journey, providing a solid foundation for subsequent analysis and decision making. Data visualization definition. Data visualization is the graphical representation of data to provide a clear and intuitive understanding of patterns, trends, and insights. It transforms raw data into visual formats, making complex information more accessible and comprehensible. Importance. Effective data visualization is crucial for conveying information in a way that is easily digestible. It enables decision makers to grasp concepts quickly, identify outliers, and communicate findings to a diverse audience. Key concepts: charts and graphs. Explanation. Charts and graphs are visual representations of data. Common types include bar charts, line charts, pie charts, and scatter plots. Example: using a bar chart to compare sales figures for different products. Color coding. Explanation. Color is used strategically to highlight specific data points, categories, or trends in a visualization. Example: using different colors to represent different sales regions in a map. Legends and labels. Explanation. Legends and labels provide context and clarity by explaining what each element in the visualization represents. Example: adding labels to data points in a scatter plot to indicate specific values. Data trends. Explanation. Visualizations help identify trends and patterns in data, such as upward or downward slopes in a line chart. Example: observing a rising trend in website traffic over a period. Interactive visualizations. Explanation. Interactive visualizations allow users to explore data dynamically, enhancing engagement and understanding. Example: a web-based map where users can click on regions to see specific information. Heat maps. Explanation. Heat maps use color intensity to represent the magnitude of values in a matrix, making it easy to identify patterns. Example: using a heat map to show customer engagement levels at different times of the day. Infographics. Explanation. Infographics combine visual elements like charts, icons, and text to convey information concisely and attractively. Example: creating an infographic to showcase key statistics from a survey. Dashboard design. Explanation. Dashboards present a collection of visualizations in a unified layout, providing a comprehensive view of data. Example: a business dashboard displaying key performance indicators KPIs like sales, expenses, and customer satisfaction. Storytelling with data. Explanation. Arranging visualizations in a logical sequence can tell a story, guiding viewers through a narrative. Example: a series of visualizations showing the progression of a project from initiation to completion. Visual hierarchy. Explanation. Establishing a visual hierarchy guides the viewer's attention to the most important elements in a visualization. Example: using font size and color to emphasize a key data point in a bar chart. Data visualization is like painting a picture of data where each element contributes to the overall understanding. By employing visual elements strategically, data visualization turns complex datasets into clear and impactful insights, facilitating informed decision making. Machine learning basics. Definition. Machine learning is a subset of artificial intelligence that focuses on the development of algorithms and statistical models that enable computer systems to learn and improve from experience without being explicitly programmed. It's like teaching a computer to make predictions or decisions based on data patterns. Importance. Machine learning allows computers to recognize patterns, make predictions, and automate decision-making processes. It finds applications in various fields, from image recognition to personalized recommendations. Key concepts. Supervised learning. Explanation. Supervised learning involves training a model on a labeled dataset where each input has a corresponding output. The model learns to map inputs to outputs. Example, teaching a model to classify emails as spam or not spam based on labeled training data. Unsupervised learning. Explanation. Unsupervised learning deals with unlabeled data aiming to discover patterns, relationships, or structures within the data. Example, clustering similar customer behaviors without predefined categories. Features and labels. Explanation. Features are the input variables used to make predictions and labels are the outputs the model aims to predict. Example, in predicting house prices, features might include square footage, number of bedrooms, and location, while the price is the label. Training and testing. Explanation. The model is trained on a portion of the data training set and then evaluated on another portion testing set to assess its performance. Example, using 80% of data to train a model and the remaining 20% to evaluate its accuracy. Classification. Explanation. Classification involves assigning predefined labels or categories to input data based on the learned patterns. Example, identifying whether an image contains a cat or a dog. Regression. Explanation. Regression predicts a continuous output such as predicting house prices rather than discrete categories. Example, predicting the temperature based on historical weather data. Overfitting and underfitting. Explanation. Overfitting occurs when a model learns noise in the training data, while underfitting occurs when it fails to capture the underlying patterns. Example, overfitting may involve memorizing specific data points rather than learning general trends. Hyperparameters. Explanation. Hyperparameters are parameters external to the model that influence its learning process, such as the learning rate or the number of hidden layers. Example, adjusting the learning rate to control the step size during model training. Validation. Explanation. Validation is the process of assessing a model's performance on an independent dataset to ensure its generalization capability. Example, using a validation set to fine-tune model parameters. Ensemble learning. Explanation. Ensemble learning combines the predictions of multiple models to improve overall performance and robustness. Example, creating a random forest by combining predictions from multiple decision trees. Machine learning basics are like building blocks for constructing intelligent systems. By understanding these concepts, practitioners can develop models capable of making predictions, recognizing patterns, and adapting to new data, thus enabling a wide range of applications in diverse domains. Feature engineering. Feature engineering is the process of certain new features or modifying existing ones to improve the performance of a machine learning model. It involves selecting, transforming, and combining features to enhance the representation of the underlying patterns in the data. Importance. Effective feature engineering can significantly impact the model's ability to learn relevant patterns, leading to improved accuracy and generalization. It helps in extracting meaningful information from raw data and optimizing feature sets for specific machine learning tasks. Key concepts. Feature selection. Explanation. Feature selection involves choosing the most relevant features for a particular task while discarding irrelevant or redundant ones. Example, in predicting house prices, selecting features like square footage and number of bedrooms while excluding less influential ones. Handling missing data. Explanation. Dealing with missing data by imputing or removing entries ensures that models are trained on complete datasets. Example, filling missing age values in a dataset with the median age of the population. Encoding categorical variables. Explanation, converting categorical variables into numerical representations so that machine learning algorithms can effectively use them. Example, transforming red, blue, and green into numerical values like 1, 2, and 3. Scaling and normalization. Explanation, scaling and normalization ensure that numerical features are on a similar scale, preventing certain features from dominating others. Example, scaling features like income and age to have similar ranges. Binning. Explanation, grouping continuous numerical data into bins or intervals to simplify patterns and improve model robustness. Example, binning ages into categories like child, teenager, adult, and senior. Creating interaction terms. Explanation, introducing new features that represent interactions between existing features to capture combined effects. Example, multiplying the number of bedrooms by the number of bathrooms to represent the total living space. Polynomial features. Explanation, introducing polynomial features by raising existing features to higher powers, allowing the model to capture nonlinear relationships. Example, adding squared or cubed terms to capture quadratic or cubic patterns in data. Time-based features. Explanation, extracting features related to time, such as day of the week or month, to capture temporal patterns. Example, adding a weekday feature for predicting daily sales. Domain-specific features. Explanation, introducing features based on domain knowledge to enhance the model's understanding of specific contexts. Example, adding a credit score utilization ratio feature in credit risk assessment. Feature importance analysis. Explanation, analyzing the importance of each feature in the model to identify which features contribute most to predictions. Example, using techniques like tree-based algorithms to assess feature importance. Feature engineering is akin to sculpting raw data into a form that maximizes the machine learning model's ability to extract meaningful insights by selecting, transforming, and creating features thoughtfully. Practitioners can enhance the model's performance and ensure it captures the most relevant information from the data. Model evaluation and metrics. Definition, model evaluation involves assessing the performance of a machine learning model using various metrics and techniques. It helps determine how well the model generalizes to new unseen data and how effectively it achieves its intended task. Importance, evaluating a model is crucial to ensure it meets the desired standards and to identify areas for improvement. Different metrics provide insights into different aspects of a model's performance, guiding decisions in the model development process. Key concepts. Accuracy. Explanation, accuracy measures the proportion of correctly classified instances among the total instances. Example, if a model correctly identifies 90 out of 100 images, the accuracy is 90%. Precision. Explanation, precision calculates the ratio of correctly predicted positive observations to the total predicted positives. Example, in a spam detection model, precision measures the accuracy of identifying spam emails among those predicted as spam. Recall, sensitivity. Explanation, recall evaluates the ability of the model to capture all the positive instances. Example, in a medical diagnosis model, recall measures how well the model identifies all actual cases of a disease. F1 score. Explanation, the F1 score is the harmonic mean of precision and recall, providing a balanced measure of a model's performance. Example, Balancing the trade-off between precision and recall in a classification task. Area under the ROC curve. Explanation. AUC ROC assesses the ability of a binary classification model to discriminate between positive and negative instances. Example. Plotting the true positive rate against the false positive rate. Mean squared error MSE. Explanation. MSE measures the average squared difference between actual and predicted values. Example. Calculating the MSE for a regression model predicting housing prices. Confusion matrix. Explanation. A confusion matrix provides a detailed breakdown of model performance showing true positives, true negatives, false positives, and false negatives. Example. Visualizing how well a model categorizes instances into different classes. Receiver operating characteristics ROC curve. Explanation. The ROC curve illustrates the trade-off between true positive rate and false positive rate at different classification thresholds. Example. Analyzing how well a binary classifier distinguishes between classes. Precision recall curve. Explanation. The precision recall curve plots recession against recall at different classification thresholds. Example. Assessing the model's performance in scenarios where precision and recall are critical. Cross-validation. Explanation. Cross-validation involves partitioning the dataset into multiple subsets, training the model on different subsets, and evaluating its performance on the remaining data. Example. Performing k-fold cross-validation to ensure robust assessment of model generalization. Model evaluation metrics provide a comprehensive view of a model's strengths and weaknesses. Choosing the right matrix depends on the nature of the task, the importance of false positive and false negatives, and the desired balance between precision and recall. Iterative evaluation and refinement are key to developing models that perform well in real-world scenarios. Regression analysis. Definition. Regression analysis is a statistical method used in machine learning to model the relationship between a dependent variable target and one or more independent variables features. It aims to understand the nature of this relationship and make predictions based on the input features. Importance. Regression analysis is essential for predicting continuous outcomes such as prices, temperatures, or sales. It provides insights into the strength and direction of relationships between variables, allowing for informed decision making. Key concepts. Linear regression. Explanation. Linear regression models the relationship between the dependent variable and one or more independent variables using a linear equation. Example. Predicting house prices based on features like square footage and number of bedrooms. Multiple regression. Explanation. Multiple regression extends linear regression to include multiple independent variables in the model. Example. Predicting a student's GPA based on hours spent studying extracurricular activities and parental education level. Coefficient of determination R squared. Explanation. R squared measures the proportion of the variance in the dependent variable explained by the independent variables. Example. An R squared value of 0.80 indicates that 80% of the variation in house prices is explained by the features in the model. Explanation. Residuals are the differences between the predicted and actual values. Analyzing residuals helps assess the model's accuracy. Example. A positive residual indicates the model underpredicted, while a negative residual means it is overpredicted. Assumptions of regression. Explanation. Regression analysis relies on certain assumptions including linearity, independence of errors, homoscedasticity, constant variance of errors, and normality of residuals. Example, checking that the residuals are evenly distributed and show no patterns. Outliers and influential points. Explanation. Outliers are data points that deviate significantly from the overall pattern, while influential points have a substantial impact on the regression model. Example, identifying a data point with an unusually high or low value that affects the regression line. Gradient descent for regression. Explanation. Gradient descent is an optimization algorithm used to find the coefficients that minimize the error in the regression model. Example, adjusting the coefficients iteratively to minimize the sum of squared residuals. Regularization, lasso and ridge regression. Explanation. Regularization techniques like lasso and ridge introduce penalty terms to prevent overfitting in regression models. Example, using lasso regression to shrink some coefficient to zero, simplifying the model. Heteroscedasticity. Explanation. Heteroscedasticity refers to the unequal variance of residuals across different levels of the independent variables. Example, residuals showing a widening or narrowing pattern as the independent variable increases. Collinearity. Explanation. Collinearity occurs when two or more independent variables are highly correlated, leading to instability in coefficient estimates. Example, identifying situations where features like height and weight are strongly correlated in a regression model. Regression analysis is a powerful tool for understanding relationships between variables and making predictions based on observed data. Careful consideration of assumptions, checking for outliers, and choosing appropriate regularization techniques are essential for building robust regression models. Classification. Definition. Classification is a type of supervised learning in machine learning that involves training a model to categorize input data into predefined classes or labels. The goal is to learn a mapping from input features to discrete output categories. Importance. Classification is widely used in various applications such as spam detection, image recognition, sentiment analysis, and medical diagnosis. It helps automate decision-making processes by assigning data points to specific categories. Key concepts. Binary classification. Explanation. Binary classification involves categorizing data into two classes or categories. Example, distinguishing between spam and non-spam emails. Multi-class classification. Explanation. Multi-class classification deals with scenarios where data can belong to more than two classes. Example, identifying different species of flowers based on features like petal length and width. Decision boundary. Explanation. The decision boundary is the boundary that separates different classes in a classification model. Example, in a two-dimensional space, the decision boundary is a line that separates data points of two classes. Confusion matrix. Explanation. A confusion matrix displays the performance of a classification model showing true positives, true negatives, false positives, and false negatives. Example, evaluating how well a model distinguishes between classes. Precision and recall. Explanation. Precision measures the accuracy of positive predictions, while recall assesses the ability to capture all positive instances. Example, precision is the ratio of true positives to the sum of true positives and false positives. F1 score. Explanation. The F1 score is the harmonic mean of precision and recall, providing a balanced measure of a model's performance. Example, balancing precision and recall in scenarios where both are crucial. Receiver operating characteristics, ROC curve. Explanation. The ROC curve illustrates The trade-off between true positive rate and false positive rate at different classification thresholds. Example, assessing the model's ability to distinguish between classes. Sport vector machine, SVM. Explanation. Sports vector machine is a classification algorithm that finds the optimal hyperplane to separate different classes in feature space. Example, using SVM for image classification. K nearest neighbors, KNN. Explanation. KNN classifies data points based on the majority class among their K nearest neighbors. Examples, assigning a data point to the most common class among its 5 nearest neighbors. Random forest. Explanation. Random forest is an ensemble learning method that combines the predictions of multiple decision trees to improve classification accuracy. Example, employing a random forest for predicting customer churn. Naive Bayes. Explanation. Naive Bayes is a probabilistic classification algorithm based on Bayes' theorem assuming independence between features. Example, classifying emails as spam or non-spam based on the occurrence of specific words. Ensemble learning. Explanation. Ensemble learning combines multiple models to improve overall classification performance. Example, creating an ensemble of decision trees for better accuracy. Classification models are essential for automating decision making in a wide range of applications. Understanding metrics like precision, recall, and F1 score, along with choosing appropriate algorithms, helps build effective models that can generalize well to new, unseen data. Clustering. Clustering is an unsupervised learning technique in machine learning that involves grouping similar data points together based on certain criteria. The goal is to discover inherent patterns or structures within the data without predefined labels. Importance. Clustering is used for various purposes such as customer segmentation, anomaly detection, and organizing large datasets into meaningful groups. It helps uncover hidden structures within data, making it easier to analyze and interpret. Key concepts. K-means clustering. Explanation. K-means is a popular clustering algorithm that partitions data into K clusters based on similarities in feature space. Example, grouping customers into clusters based on their purchasing behavior. Hierarchical clustering. Explanation. Hierarchical clustering builds a tree-like hierarchy of clusters, allowing for different levels of granularity. Example, visualizing the hierarchical relationships between species in a biological taxonomy. Density-based special clustering of applications with noise, DBSCAN. Explanation. DBSCAN identifies clusters based on dense regions in the data, separating areas of lower density. Example, detecting regions of high and low population density in a geographical dataset. Agglomerative versus divisive clustering. Explanation. Agglomerative clustering starts with individual data points and merges them into clusters, while divisive clustering begins with one large cluster and divides it into smaller ones. Example, agglomerative clustering, merging individual words into topic clusters in a document. Centroid-based versus density-based clustering. Explanation. Centroid-based clustering relies on the notion of a central point, centroid, for each cluster, while density-based clustering identifies clusters based on regions of varying data density. Example, K-means is a centroid-based method while DBSCAN is density-based. Explanation. The silhouette score quantifies how well separated clusters are, ranging from 1 incorrect clustering to 1 well separated clusters. Example, assessing the compactness and Separability of clusters. Elbow method explanation. The elbow method helps determine the optimal number of clusters in k-means by identifying the point where additional clusters provide diminishing returns in explaining variance. Example, selecting the appropriate number of customer segments for marketing strategies. Cluster validation explanation. Cluster validation involves assessing the quality of clustering results using metrics like purity, entropy, or adjusted RAND index. Example, evaluating the accuracy of clustering results in a customer segmentation task. Feature scaling in clustering explanation. Feature scaling ensures that all features contribute equally to the clustering process, preventing dominance by features with larger scales. Example, scaling features like income and age to have similar magnitude. Interpretability of clusters explanation. Interpreting clusters involves understanding the characteristics of commonalities within each cluster to derive actionable insights. Examples, identifying common behaviors among users in a cluster for targeted marketing. Applications of clustering explanation. Clustering finds applications in diverse fields including customer segmentation, image segmentation, and anomaly detection. Example, grouping news articles into topics for personalized content recommendations. Clustering is a powerful tool for organizing and extracting patterns from data without labeled categories. Choosing the right clustering algorithm and evaluating the quality of clusters are crucial steps in leveraging unsupervised learning techniques for various applications. Natural language processing (NLP). Natural language processing is a branch of artificial intelligence that focuses on the interaction between computers and humans through natural language. It involves the development of algorithms and models that enable computers to understand, interpret, and generate human language. Importance. Natural language processing plays a crucial role in bridging the gap between human communication and machine understanding. It is used in applications such as language translation, sentiment analysis, chatbots, and text summarization, making it a fundamental technology for processing and extracting meaning from textual data. Key concepts. Tokenization explanation. Tokenization is the process of breaking down text into smaller units, such as words or subword units, tokens, for analysis. Example, breaking the sentence I love NLP into tokens I love NLP. Part of speech tagging. Explanation. Part of speech tagging assigns grammatical labels such as noun, verb, adjective to each word in a sentence. Example, tagging the sentence the cat is sleeping with parts of speech, article, noun, verb, verb. Named entity recognition (NER). Explanation. NER identifies and classifies entities such as names of people, organizations, locations in text. Example, recognizing Apple as an organization in the sentence Apple Inc. is a technological company. Sentiment analysis. Explanation. Sentiment analysis determines the sentiment expressed in a piece of text such as positive, negative, or neutral. Example, analyzing social media comments to identify whether they express positive or negative sentiment. Text classification. Explanation. Text classification assigns predefined categories or labels to documents or sentences. Example, categorizing emails as spam or not spam based on their content. Word embeddings. Explanation. Word embeddings represent words as dense vectors in a continuous vector space, capturing Semantic relationships. Example, representing words like king and queen as vectors with similar distances and directions. Machine translation. Explanation. Machine translation involves automatically translating text from one language to another. Example, translating a sentence from English to French using NLP models. Syntax and grammar parsing. Explanation. Syntax and grammar parsing analyzes the grammatical structure of sentences, identifying relationships between words. Example, parsing the sentence, the quick brown fox jumps over the lazy dog. Text generation. Explanation. Text generation creates human-like text based on patterns and context learned from existing data. Example, generating coherent paragraphs or sentences using language models. Co-reference resolution. Explanation. Co-reference resolution identifies when different words or phrases in a text refer to the same entity. Example, resolving that he refers to John in the sentence, John likes ice cream, he eats it every day. Question answering. Explanation. Question answering systems process questions and provide relevant answers based on textual information. Example, answering user queries about a given text or document. NLP enables computers to understand and work with human language, opening up possibilities for applications that involve text processing, understanding user intent, and generating human-like responses. The development of advanced NLP models, such as transformers, has significantly improved the capabilities of language understanding in artificial intelligence systems. Time series analysis. Definition. Time series analysis is a statistical and mathematical approach to understanding and interpreting data points collected over time. It involves studying the temporal patterns and trends within a dataset to make predictions, identify anomalies, or gain insights into the underlying dynamics of the time-varying phenomena. Importance. Time series analysis is crucial for various applications, including finance, economics, weather forecasting, stock market analysis, and signal processing. By examining how data evolves over time, analysts can uncover patterns, seasonality, and relationships that inform decision making and forecasting. Key concepts. Time series data. Explanation. Time series data consists of observations collected, recorded, or measured at regular intervals over time. Example, daily stock prices, monthly sales figures, hourly temperature readings. Trend analysis. Explanation. Trend analysis involves identifying the long-term movement or direction in a time series. Example, recognizing a gradual increase in sales over several years. Seasonal decomposition. Explanation. Seasonal decomposition separates a time series into its trend, seasonal, and residual components to analyze each separately. Example, identifying regular patterns like increased sales during holiday seasons. Autocorrelation function, ACF. ACF measures the correlation between a time series and its lagged values at different time intervals. Example, assessing how today's stock price correlates with yesterday's or last week's. Moving averages. Explanation. Moving averages smooth out short-term fluctuations in a time series, making it easier to identify trends. Example, calculating a 7-day moving average to highlight weekly trends in sales data. Exponential smoothing. Explanation. Exponential smoothing assigns different weights to past observations, giving more importance to recent data. Example, forecasting future stock prices based on a weighted average of historical prices. Stationarity. Explanation. A time series is stationary if its statistical properties such as mean and variance remain constant over time. Example. Checking for stationarity in financial time series data. ARIMA models. Explanation. ARIMA, autoregressive integrated moving average, models combine autoregressive and moving average components to model time series data. Example, using ARIMA to predict future stock prices based on historical trends. Seasonal ARIMA, SARIMA models. Explanation. SARIMA extends ARIMA models to account for seasonal patterns in time series data. Example, forecasting monthly sales with consideration for yearly seasonality. Forecasting. Explanation. Forecasting involves predicting future values of a time series based on historical data and established patterns. Example, predicting next month's temperature or next quarter's sale. Time series cross-validation. Explanation. Cross-validation techniques for time series ensure that models are evaluated in a way that accounts for the temporal nature of the data. Example, splitting time series data into training and testing sets while preserving chronological order. Time series analysis provides valuable tools and techniques for understanding and predicting trends in temporal data, whether for business planning, financial forecasting, or scientific research. The insights gained from time series analysis contribute to informed decision making and strategy development. Dimensionality reduction. Definition. Dimensionality reduction is a technique in machine learning and statistics that involves reducing the number of input variables or features in a dataset. The goal is to simplify the dataset while retaining as much relevant information as possible. This is particularly useful when dealing with high dimensional data where the number of features is large. Importance. Reducing dimensionality has several benefits, including mitigating the curse of dimensionality, speeding up training times for machine learning models, improving model interpretability, and uncovering underlying patterns in the data. Key concepts. Curse of dimensionality. Explanation. The curse of dimensionality refers to the challenges and increased complexity that arise when working with high dimensional data. Example, in high dimensional spaces, data points become sparsely distributed and distances between points lose meaning. Principal component analysis, PCA. Explanation. PCA is a popular technique for linear dimensionality reduction. It transforms the original features into a new set of uncorrelated variables called principal components. Example, reducing the dimensions of a dataset while preserving the variance in the data. Singular value decomposition, SVD. Explanation. SVD is a mathematical technique that decomposes a matrix into three other matrices, facilitating dimensionality reduction in a manner similar to PCA. Example, decomposing a user item interaction matrix in collaborative filtering for recommendation system. T distributed stochastic neighbor embedding, TSNE. Explanation. TSNE is a non-linear dimensionality reduction technique that focuses on preserving local relationships between data points in the original space. Example, visualizing high-dimensional data clusters into a two-dimensional space for exploration. Autoencoders. Explanation. Autoencoders are neural network architectures designed for unsupervised learning. They consist of an encoder and decoder, and the middle layer represents the reduced dimensional space. Example, using autoencoders to learn a compressed representation of images for image reconstruction. Manifold learning. Explanation. Manifold learning techniques aim to capture the intrinsic geometry of high dimensional data by mapping it to a lower dimensional manifold. Example, isomap, isometric mapping for preserving geodesic distances in the reduced space. Feature selection versus dimensionality reduction. Explanation. While dimensionality reduction reduces the number of features, feature selection retains a subset of the original features. Example, selecting the most relevant features based on their importance scores. Explained variance. Explanation. Explained variance measures the proportion of the dataset's total variance captured by the reduced set of dimensions. Example, assessing how much information is retained after applying PCA. Overfitting and dimensionality reduction. Explanation. Reducing dimensionality can mitigate overfitting, especially when dealing with a small dataset and a large number of features. Example, regularizing a model by reducing the number of features to prevent it from fitting noise. Applications of dimensionality reduction. Explanation. Dimensionality reduction is applied in various domains, including image processing, genetics, finance, and natural language processing. Example, reducing the dimensions of an image for faster processing without losing critical visual features. Dimensionality reduction techniques play a vital role in pre-processing and analyzing high-dimensional data, contributing to improved model performance, interpretability, and computational efficiency. The choice of a specific technique depends on the characteristics of the data and the goals of the analysis. Ensemble learning. Definition. Ensemble learning is a machine learning approach that involves combining the predictions of multiple models to improve overall performance and robustness. By leveraging the strengths of different models or training the same model on different subsets of the data, ensemble methods aim to achieve better generalization and reduce the risk of overfitting. Importance. Ensemble learning is widely used in practice because it often leads to more accurate and reliable predictions compared to individual models. It helps address the limitations of single models and enhances the overall predictive power of the system. Ensemble methods. Explanation. Ensemble methods include various techniques for combining multiple models. Common approaches include bagging, boosting, and stacking. Example, random forest and gradient boosting are popular ensemble methods. Bagging, bootstrap, aggregating. Explanation. Bagging involves training multiple instances of the same model on different bootstrap samples of the training data and averaging or voting on predictions. Example, random forest, which aggregates multiple decision trees trained on different subsets of the data. Boosting. Explanation. Boosting focuses on training multiple weak learners sequentially, where each subsequent model corrects the errors of the previous one. Example, AdaBoost and gradient boosting algorithms. Random forest. Explanation. Random forest is an ensemble learning method based on bagging where multiple decision trees are trained independently and their predictions are combined through averaging or voting. Example, predicting the outcome of a medical diagnosis based on various features. Gradient boosting. Explanation. Gradient boosting builds an ensemble of weak learners sequentially, with each learner addressing the residuals of the combined model. Example, predicting housing prices based on multiple features. Stacking. Explanation. Stacking involves training multiple diverse models and a meta model is trained to combine their predictions. Example, combining the predictions of a linear regression model, a support vector machine, and a neural network using another model. Voting classifiers. Explanation. Voting classifiers combine the predictions of multiple models through a majority vote for classification or averaging for regression. Example, ensemble of decision trees, support vector machines, and k-nearest neighbors for classification. Model diversity. Explanation. Model diversity is crucial in ensemble learning to ensure that individual models make different errors, leading to a more robust combined model. Example, combining a decision tree, a linear model, and a neural network for classification. Ensemble size. Explanation. The number of models in an ensemble can impact performance. Increasing ensemble size may improve accuracy, but there is a diminishing return beyond a certain point. Example, training an ensemble with 100 decision trees for a specific task. Hyperparameter tuning. Explanation. Ensemble methods often have hyperparameters that need to be tuned for optimal performance. Example, tuning the learning rate and the number of estimators in a gradient boosting algorithm. Ensemble learning is a powerful technique for improving the accuracy and robustness of machine learning models. It is widely used in various applications, from classification and regression to anomaly detection and recommendation systems. Understanding the principles and techniques of ensemble learning is valuable for practitioners seeking to enhance the performance of their machine learning models. Big data technologies. Definition. Big data technologies refer to the diverse set of tools, frameworks, and technologies designed to process, store, and analyze large and complex data sets. These technologies are essential for managing the immense volumes of data generated in various industries, enabling organizations to extract valuable insights and make data-driven decisions. Apache Flink. Explanation. Apache Flink is an open-source stream processing framework for big data processing and analytics. It supports event time processing and has built-in support for stateful computations. Example, real-time analytics on streaming data from IoT devices using Flink. Apache Kafka. Explanation. Apache Kafka is a distributed streaming platform for building real-time data pipelines and streaming applications. It provides high throughput, fault tolerance, and scalability. Example, building a real-time data ingestions pipeline for processing logs or monitoring events. NoSQL database. Explanation. NoSQL databases are designed for handling large volumes of unstructured or semi-structured data. Examples include MongoDB, Cassandra, and Couchbase. Example, storing and retrieving data from a NoSQL database for a web application. Apache Cassandra. Explanation. Apache Cassandra is a highly scalable and distributed NoSQL database known for its ability to handle large amounts of data across multiple commodity servers. Example, storing and retrieving time series data or user profiles in Cassandra. Hive. Explanation. Apache Hive is a data warehousing and SQL-like query language for Hadoop. It allows users to query data stored in Hadoop using SQL syntax. Example, analyzing and reporting on large datasets stored in Hadoop using Hive queries. HBase. Explanation. Apache HBase is distributed, scalable, and consistent NoSQL database built on top of Hadoop. It is designed for real-time read and write access to large datasets. Example, storing and retrieving sensor data from IoT devices in HBase. Distributed storage systems. Explanation. Distributed storage systems like Amazon S3, Google Cloud Storage, and Azure BLOB storage are used for storing and retrieving large volumes of data across multiple nodes. Examples: storing and accessing data in the cloud for scalability and durability. Data lakes. Explanation: data lakes are centralized repositories that allow organizations to store structured and unstructured data at any scale. They often use technologies like Apache Hadoop and Apache Spark. Example: building a data lake to store and analyze diverse datasets from various sources. Containerization and orchestration. Explanation: technologies like Docker for containerization and Kubernetes for orchestration provide scalable and efficient ways to deploy and manage big data applications. Example: running and managing multiple instances of a big data application using Docker and Kubernetes. Machine learning framework. Explanation: big data technologies often integrate with machine learning frameworks like TensorFlow, PyTorch, and scikit-learn for building and deploying machine learning models. Example: training and deploying predictive models on large datasets using TensorFlow on a distributed computing environment. Big data technologies continue to evolve, and the choice of tools depends on specific use cases, data requirements, and scalability needs. These technologies collectively form the foundation for organizations to harness the power of big data for analytics, insights, and decision making. Database management. Definition: database management refers to the systematic organization, storage, retrieval, and maintenance of data in a structured format. It involves the use of database management systems (DBMS) to create, manage, and optimize databases for efficient data handling and retrieval. Key concepts: database management system (DBMS). Explanation: a DBMS is software that provides an interface for interacting with databases. It facilitates the creation, modification, and querying of databases while ensuring data integrity and security. Example: Oracle database, MySQL, Microsoft SQL Server. Relational database. Explanation: a relational database organizes data into tables with rows and columns. It uses relationships between tables to represent and store data. Example: storing customer information in a relational database with tables for customers, orders, and products. SQL, structured query language. Explanation: SQL is a standard language for interacting with relational database. It is used for querying, updating, and managing data. Example: writing SQL queries to retrieve information from a database, that is select star from customers where country is equal to USA. Data modeling. Explanation: data modeling involves designing the structure of a database, defining tables, relationships, and constraints to represent the data accurately. Example: creating an entity relationship diagram (ERD) to model the relationships between entities in a database. Normalization. Explanation: normalization is the process of organizing data to eliminate redundancy and improve data integrity. It involves breaking down tables and relationships to ensure data consistency. Example: breaking single table with customer information into separate tables for customers and orders. Indexes. Explanation: indexes are data structures that enhance the speed of data retrieval operations on a database by providing quick access to specific rows. Example: creating an index on the email column of a user table for faster email-based searches. Transactions. Explanation: a transaction is a sequence of one or more operations that are executed as a single unit. It ensures the consistency and integrity of the database. Example: transferring funds between two bank accounts where both debit and credit operations must occur together. Explanation: regularly backing up database and having recovery mechanisms in place ensure that data can be restored in case of accidental deletion corruption, or system failure. Example, scheduling daily backups of a customer database and testing the restoration process. Data warehousing. Explanation. Data warehousing involves the collection, storage, and management of large volumes of data from various sources for business intelligence and analysis. Example, creating a data warehouse to consolidate and analyze sales data from multiple retail locations. NoSQL databases. Explanation. NoSQL databases are designed to handle unstructured or semi-structured data and provide flexible schema designs. Example, storing and retrieving data in a MongoDB document database for a content management system. Database scalability. Explanation. Database scalability refers to the ability of a database system to handle an increasing amount of data, users, or transactions. Example, implementing sharding or partitioning to distribute data across multiple servers for improved scalability. Data migration. Explanation. Data migration involves transferring data from one database or system to another. It requires careful planning and execution to avoid data loss or corruption. Example, migrating customer data from an on-premise database to a cloud-based database. Database management is a critical aspect of information systems, providing a structured and efficient way to organize and access data. Effective database management ensures data accuracy, security, and availability for applications, analytics, and decision-making processes within organizations. Cloud computing. Cloud computing is a technology paradigm that involves delivering computing services including servers, storage, databases, networking, analytics, software, and intelligence over the internet, the cloud, to offer flexible resources, scalability, and cost efficiency. Users can access and utilize these services on demand without the need for extensive infrastructure management. Key concepts. Service models. Explanation. Cloud computing offers various service models including infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. Example, Amazon Web Services, AWS, provides IaaS with virtual machines, PaaS with platforms like AWS, Elastic, Beanstalk, and SaaS with applications like Amazon S3. Deployment models. Explanation. Cloud services can be deployed in different models: public cloud accessible to the general public, private cloud dedicated to a single organization, hybrid cloud combining public and private clouds, and multi-cloud using services from multiple cloud providers. Example, Microsoft Azure provides a public cloud, Azure Stack for private cloud, and supports hybrid cloud scenarios. Virtualization. Explanation. Virtualization enables the creation of virtual instances of computing resources such as servers, storage, and networks, allowing efficient utilization and management of physical hardware. Example, using hypervisors like VMware or Hyper-V to run multiple virtual machines on a single physical server. Scalability. Explanation. Cloud services provide scalability, allowing users to increase or decrease resources based on demand. It ensures optimal performance and cost efficiency. Example, scaling up the number of server instances during high traffic periods and scaling down during low traffic periods. Elasticity. Explanation. Elasticity is the ability to automatically scale resources up or down in response to changes in demand, ensuring that the right amount of resources is available at all times. Example, auto-scaling configurations to add or remove instances based on traffic patterns. On-demand self-service. Explanation, cloud services are available on demand, allowing users to provision and manage resources without human intervention from the service provider. Example, provisioning virtual machines, storage or databases through a cloud provider's console or API. Resource pooling. Explanation, cloud providers pool computing resources to serve multiple customers, dynamically allocating and reallocating resources based on demand. Example, shared use of computing resources such as CPU, memory, and storage by multiple virtual machines. Metered services. Explanation, cloud computing services are often metered and users pay for the resources they consume. This pay-as-you-go model allows cost optimization. Example, paying for the amount of storage used, data transferred, or compute hours consumed. APIs, application programming interfaces. Explanation, cloud services expose APIs that allows developers to interact with and control various cloud resources programmatically. Example, using APIs to automate the deployment and management of cloud resources. Security and compliance. Explanation, cloud providers implement security measures to protect data and infrastructure. Compliance certifications ensure adherence to industry and regulatory standards. Example, encryption of data in transit and at rest, and compliance with standards like ISO 27001 or HIPAA. Containers and orchestration. Explanation, containers like Docker and orchestration tools like Kubernetes facilitate the deployment and management of applications in cloud environments. Example, deploying microservices using containerization and orchestrating their interactions with Kubernetes. Serverless computing. Explanation, serverless computing allows developers to focus on writing code without managing server infrastructure. Cloud providers automatically handle scaling and resource allocation. Example, AWS Lambda, where developers upload code functions that run in response to events without provisioning servers. Cloud computing has transformed the way organizations build, deploy, and scale applications. It offers agility, cost savings, and innovation opportunities by providing a flexible and scalable infrastructure that aligns with modern computing needs. Experimentation and A/B testing. Definition. Experimentation and A/B testing are methodologies used in data-driven decision-making to assess the impact of changes in a controlled environment. These techniques involve comparing two or more variations of a system, feature, or process to determine which performs better in terms of user engagement, conversion rates, or other relevant metrics. Key concepts. Experiment design. Explanation. Experimental design involves defining the goals, metrics, and variations to be tested. It includes selecting a representative sample, establishing a control group, and ensuring randomization. Example, designing an A/B test to compare two versions of a website landing page to measure the click-through rate. Control group. Explanation. The control group is a subset of the audience that experiences the existing or default version of a system, serving as a baseline for comparison with the experimental group. Example, in an A/B test for a mobile app, the control group uses the current app version without any changes. Explanation. The experimental group experiences the modified version or new feature being tested. The performance of this group is compared to the control group to evaluate the impact of the changes. Example, the experimental group in an A/B test might see a redesigned user interface in an e-commerce app. Randomization. Explanation. Randomization ensures that participants are assigned to the control or experimental group randomly, minimizing biases and ensuring a representative sample. Example, randomly selecting users to receive either version A or version B of an email campaign. Matrix and Key Performance Indicators, KPIs. Explanation. Matrix and KPIs are the quantifiable measures used to evaluate the success of an experiment. They could include conversion rates, engagement levels, revenue, or other relevant indicators. Example, using matrix like click-through rate, CTR, or conversion rate to assess the effectiveness of a website redesign. Statistical significance. Explanation. Statistical significance is a measure that indicates whether observed differences in outcomes between groups are likely due to actual effects or are merely chance occurrences. Example, calculating p-values to determine if the differences in engagement rates between two versions are statistically significant. Hypothesis testing. Explanation. Hypothesis testing involves formulating a hypothesis about the expected outcomes of an experiment and using statistical methods to assess whether the observed results support or reject the hypothesis. Example, formulating a hypothesis that a new call to action button will lead to a higher conversion rate and testing it through experimentation. Duration of experiment. Explanation. Determining the appropriate duration of an experiment is crucial to capture sufficient data and account for potential fluctuations in user behavior over time. Example, running an A/B test for a week to capture different days of the week and potential variations in user behavior. Segmentation. Explanation. Segmenting the audience based on specific characteristics, that is demographics, location, allows for a more nuanced analysis of the experiment's impact on different user groups. Example, analyzing A/B test results separately for new users and returning users. Ethical considerations. Explanation. Ethical considerations involve ensuring that experiments are conducted in a transparent and responsible manner with respect for user privacy and well-being. Example, clearly communicating to participants that they are part of an experiment and obtaining informed consent. Iterative testing. Explanation. Continuous learning from experiments leads to iterative testing, where insights gained from one experiment inform the design of subsequent tests for continuous improvement. Example, using the findings of an A/B test on email subject lines to refine future email marketing strategies. Experimentation and A/B testing are valuable tools for businesses and organizations seeking to optimize their products, services, or user experiences. By systematically testing variations and analyzing results, teams can make informed decisions, enhance user satisfaction, and achieve better overall performance. Ethics in data science. Definition. Ethics in data science involves considering the moral implications, societal impacts, and responsible practices associated with the collection, analysis, and application of data. It encompasses principles and guidelines to ensure that data-driven decision-making aligns with ethical standards, respects privacy, and avoids potential biases or harm. Key concepts. Privacy. Explanation. Privacy concerns the protection of individuals' personal information. Data scientists must handle data responsibly, obtain informed consent, and implement measures to safeguard privacy. Example, anonymizing and encrypting sensitive personal information in datasets to prevent unauthorized access. Fairness and bias. Explanation. Ensuring fairness involves avoiding biased outcomes in data analysis and model predictions. Data scientists should address biases in data collection and algorithmic decision making. Example, regularly auditing machine learning models for biased predictions and taking corrective actions to mitigate biases. Transparency. Explanation. Transparency involves making the data science process and algorithms understandable and accessible. Openly communicating methods, assumptions, and potential limitations enhances accountability. Example, providing clear documentation and explanations for how data is collected, processed, and used in a given analysis. Informed consent. Explanation. Informed consent requires individuals to be aware of their data will be used before it is collected. Obtaining clear and explicit consent is crucial for ethical data practices. Example, clearly informing users about data collection practices and obtaining their consent before collecting personal information. Accountability. Explanation. Accountability involves taking responsibility for the ethical implications of data-driven decisions. Data scientists and organizations should be accountable for the consequences of their analysis. Example, establishing protocols for handling errors or unintended consequences in data analysis and models. Data governance. Explanation. Data governance focuses on establishing policies, standards, and procedures for managing and protecting data throughout its life cycle. It ensures responsible data management. Example, implementing data governance frameworks to define rules, responsibilities, and ethical guidelines for handling data. Data security. Explanation. Data security involves safeguarding data from unauthorized access, breaches, or theft. Protecting data integrity and confidentiality is crucial for ethical data practices. Example, employing encryption, access controls, and secure storage methods to protect sensitive information. Data ownership. Explanation. Clarifying data ownership is important for ethical data practices. Individuals should have control over their own data, and organizations should respect ownership rights. Example, clearly stating in terms of service agreements how user-generated data will be owned and used. Social impact. Explanation. Considering the broader social impact of data science activities in essential, ethical data scientists strive to contribute positively to society and minimize negative consequences. Example, assessing how a data-driven decision might disproportionately affect certain groups or communities and taking steps to mitigate negative impacts. Regulatory compliance. Explanation. Adhering to relevant laws and regulations is a fundamental aspect of ethics in data science. Compliance ensures that data practices align with legal and ethical standards. Example, ensuring that data collection, storage, and processing comply with regulations such as GDPR or HIPAA. Continuous learning. Explanation. The field of data science evolves and ethical data scientists engage in continuous learning to stay informed about emerging ethical challenges, technologies, and best practices. Example, participating in workshops, training, or forums on ethical considerations in data science. Stakeholder engagement. Explanation. Engaging with stakeholders, including those whose data is being analyzed, fosters transparency and accountability. Ethical data practices involve considering the perspectives of all relevant stakeholders. Example, soliciting feedback from users or affected communities on data collection and usage policy. Ethics in data science is a multi-dimensional concept that requires ongoing attention and commitment from practitioners and organizations. By integrating ethical considerations into every stage of the data science life cycle, professionals can contribute to responsible and socially beneficial data practices. Deep learning definition. Deep learning is a subfield of machine learning that focuses on the development and training of neural networks, particularly deep neural networks with multiple layers deep architectures. It aims to enable machines to learn and make decisions by simulating the human brain's neural networks, allowing them to automatically learn representations of data through hierarchical layers of abstraction. Key concepts. Neural networks. Explanation. Neural networks are computational models inspired by the structure and function of the human brain. In deep learning, these networks consist of interconnected layers of nodes, neurons, that process and transform input data. Example, a deep neural network for image recognition with layers responsible for detecting edges, shapes, and object features. Deep architectures. Explanation. Deep architectures refer to neural networks with multiple layers, allowing the model to learn complex and hierarchical representations of data. Deep learning often involves architectures with many hidden layers. Example, convolutional neural networks (CNNs) and recurrent neural networks (RNNs) are common deep architectures. Feature learning. Explanation. Deep learning excels at automatic feature learning, where the model learns to extract relevant features from raw data without manual feature engineering. This is particularly beneficial for unstructured data like images and text. Example, in natural language processing, a deep learning model can learn to represent words in a way that captures semantic relationships. Backpropagation. Explanation. Backpropagation is the training algorithm used in deep learning. It involves iteratively adjusting the weights of the neural network based on the difference between predicted and actual outputs, minimizing the error. Example, during backpropagation, the weights in a neural network are updated to reduce the difference between predicted and actual outcomes. Activation functions. Explanation. Activation functions introduce non-linearity to neural networks, allowing them to model complex relationships. Common activation functions include ReLU, rectified linear unit, and sigmoid. Example, applying the ReLU activation function to introduce non-linearity in the hidden layers of a neural network. Convolutional neural networks, CNNs. CNNs are specialized deep learning architectures designed for processing grid-like data, such as images. They use convolutional layers to automatically learn special hierarchies of features. Example, CNNs are widely used in image recognition tasks, detecting patterns and objects in images. Recurrent neural networks, RNNs. Explanation. RNNs are designed for processing sequential data, allowing information to be passed between time steps. They are well suited for tasks like natural language processing and time series prediction. Example, RNNs can be used for predicting the next word in a sentence or forecasting stock prices. Transfer learning. Explanation. Transfer learning involves using pre-trained models on one task as a starting point for a different but related task. It leverages knowledge gained from one domain to improve performance in another. Example, using a pre-trained image classification model on a large dataset and fine-tuning it for a specific classification task with a smaller dataset. Generative models. Explanation. Generative models in deep learning generate new data points that resemble the training data. Variational autoencoder VAES and generative adversarial networks GANS are common generative models. Example, GANS can generate realistic images such as faces by learning the distribution of the training data. Reinforcement learning explanation. Deep learning is also applied in reinforcement learning, where agents learn to make sequential decisions in an environment by receiving feedback in the form of rewards. Example, training a deep reinforcement learning model to play games by learning optimal strategies through trial and error. Natural language processing explanation. Deep learning has shown remarkable success in NLP tasks such as sentiment analysis, machine translation, and question answering by learning intricate language representations. Example, using deep learning models like transformers for language understanding and generation tasks. Self-supervised learning explanation. Self-supervised learning involves training models on tasks where the labels are generated from the input data itself. It leverages unlabeled data to learn useful representations. Example, training a model to predict masked words in a sentence where the masked words are sampled from the input text. Deep learning has achieved groundbreaking results in various domains, including computer vision, speech recognition, and natural language processing. Its ability to automatically learn hierarchical representations from data has contributed to significant advancements in artificial intelligence. Reinforcement learning definition. Reinforcement learning is a type of machine learning paradigm where an agent learns to make sequential decisions by interacting with an environment. The agent receives feedback in the form of rewards or punishments based on the actions it takes, and its objective is to learn a policy that maximizes the cumulative reward over time. Key concepts. Agent explanation. The agent is the entity that learns and makes decisions within an environment. It takes actions, receives feedback, and updates its strategy to achieve the goal. Example, in a game playing scenario, the game playing algorithms or artificial intelligence is the agent. Environment explanation. The environment is the external system or context with which the agent interacts. It provides the context for the agent's actions and determines the outcomes based on those actions. Example, in a robotic control setting, the physical environment where the robot operates is the environment. State explanation. The state represents the current situation or configuration of the environment. It is the information the agent uses to make decisions. Example, in a chess game, the arrangement of pieces on the board is the state. Action explanation. An action is a decision or move that the agent can take in a given state. The set of all possible actions constitutes the action space. Example, in robotic navigation scenario, actions could be moving forward, turning left, or turning right. Reward explanation. A reward is a numerical feedback signal that the agent receives from the environment after taking an action in a specific state. It indicates the immediate desirability of the action. Example, in a game, winning might result in a positive reward, while losing could result in a negative reward. Policy explanation. The policy is a strategy or mapping from states to actions that the agent learns. It defines the agent's behavior in the environment. Example, in a self-driving car, the policy determines how the car should react in different traffic situations. Value function explanation. The value function estimates the expected cumulative reward that an agent can obtain from a given state or state action pair. It guides the agent in making decisions. Example, in a board game, the value function might assess the desirability of a move based on potential future outcomes. Exploration versus exploitation. Explanation. Balancing exploration, trying new actions to discover their effects, and exploitation, choosing known actions with high rewards, is a key challenge in reinforcement learning. Example, a restaurant goer deciding between trying a new dish, exploration, or ordering a favorite, exploitation. Markov decision process, MDP. Explanation. Reinforcement learning problems are often formulated as Markov decision processes, where the next state depends only on the current state and action, not on the sequence of previous states and actions. Example, a game where the outcome depends only on the current state of the board and the move just made. Discount factor. Explanation. The discount factor in reinforcement learning represents the reference for obtaining rewards sooner rather than later. It influences the agent's consideration of future rewards. Example, in financial decisions, a discount factor reflects the time value of money. Q learning. Explanation. Q learning is a model-free reinforcement learning algorithm that learns the value of taking a specific action in a given state. It is based on updating a Q value table. Example, Q learning could be used to train an agent to play a simple game by learning the best actions for each state. Deep reinforcement learning, DRL. Explanation. DRL involves combining reinforcement learning with deep neural networks to handle high-dimensional state spaces. It has been successful in complex tasks like playing video games. Example, using a deep neural network to learn a policy for playing a complex game such as Go or DOTA 2. Reinforcement learning is applicable in scenarios where an agent learns to navigate dynamic and uncertain environments, making sequential decisions to achieve long-term objectives. It has been successfully employed in various domains, including robotics, gaming, finance, and autonomous systems. Anomaly detection. Definition. Anomaly detection, also known as outlier detection, is a data analysis technique used to identify patterns or instances that deviate significantly from the expected or normal behavior. Within a dataset, anomalies are often indicative of errors, unusual events, or potential security threats. Key concepts: normal behavior. Explanation. Anomaly detection assumes that the majority of the data represents normal behavior. Deviation from this normal behavior are considered anomalies. Example, in network traffic data, normal behavior might include regular patterns of data transfers and communication. Anomalies. Explanation. Anomalies are instances or patterns in the data that differ significantly from the expected normal behavior. They can be indicative of errors, fraud, or unusual events. Example, unusual spikes in website traffic or unexpected fluctuations in stock prices could be anomalies. Unsupervised learning. Explanation. Anomaly detections is often approached as an supervised learning problem, where the algorithm learns the normal behavior without explicit labels for anomalies. Example, clustering algorithms or statistical methods are used to identify patterns in the absence of labeled anomalies. Supervised learning for anomalies. Explanation. In some cases, supervised learning can be used for anomaly detection with labeled data, where the model is trained on both normal and anomalous instances. Example, using a dataset with labeled instances of fraudulent transactions to train supervised anomaly detection model. Statistical methods. Explanation. Statistical techniques such as mean, median, standard deviation, or z-scores can be employed to identify anomalies based on deviations from the statistical properties of the data. Example, flagging data points that fall outside specified range of standard deviations from the mean. Clustering. Explanation. Clustering algorithms group similar data points together. Anomalies may be detected by identifying instances that do not fit well into any cluster. Example, using k-means clustering to group similar data points and identifying data points distant from cluster centers as anomalies. Isolation forests. Explanation. Isolation forests are an ensemble learning technique designed for anomaly detection. They work by isolating anomalies through the creation of random decision trees. Example, isolation forests can be used to identify outliers in a dataset by measuring the number of splits needed to isolate data points. One class SVM. Explanation. One class support vector machines SVM learn a representation of normal instances and classify anything dissimilar as anomalous. Example, training a one class SVM on normal instances of server performance matrix to detect anomalous behavior. Autoencoders. Explanation. Autoencoders are a type of neural network that learns to encode and decode data. Anomalies can be detected by observing reconstruction errors. Example, training an autoencoder on normal instance of images and identifying instances with high reconstruction errors as anomalies. Time series anomaly detection. Explanation. Anomaly detection in time series data involves identifying deviations from expected temporal patterns. Techniques like moving averages or dynamic time warping can be used. Example, detecting anomalies in temperature readings over time, such as sudden spikes or drops. Domain-specific features. Explanation. Anomaly detection often benefits from incorporating domain-specific features and knowledge to better distinguish between normal and anomalous behavior. Example, in healthcare, abnormal physiological readings might be detected by combining multiple relevant features. Thresholding. Explanation. Setting a threshold for acceptable deviation from normal behavior can be a simple yet effective method for identifying anomalies. Example, considering any data point with a value exceeding a specified threshold as an anomaly. Anomaly detection is crucial in various domains, including cybersecurity, fraud detection, quality control, and system monitoring, where identifying unusual patterns or outliers is essential for maintaining the integrity and security of systems and processes. Optimization algorithms. Definition. Optimization algorithms are techniques used to find the best possible solution or set of parameters that optimize a given objective function. These algorithms play a crucial role in various fields, including machine learning, where they are employed to minimize or maximize a cost or utility function during model training. Key concepts. Objective function. Explanation. The objective function, also known as the cost function or loss function, quantifies the performance of a model or system. Optimization algorithms aim to find the input values that minimize or maximize this function. Example, in linear regression, the objective function could be the mean squared error between predicted and actual values. Local minimum and global minimum. Explanation. A local minimum is the lowest point in the objective function within a specific neighborhood, while a global minimum is the absolute lowest point across the entire function. Example, in a hilly terrain objective function, a local minimum is a low point in a specific hill, while the global minimum is the lowest valley. Gradient descent. Explanation. Gradient descent is an iterative optimization algorithm that minimizes the objective function by adjusting parameters in the direction of the steepest negative gradient. Example, adjusting model weights in a direction that reduces the cost function gradient. Stochastic gradient descent, SGD. Explanation. SGD is a variant of gradient descent that uses a random subset of data, mini batch, to compute the gradient and update parameters. It introduces randomness which can speed up convergence. Example, training a neural network by randomly selecting small batches of data for each iteration. Batch gradient descent. Explanation. Batch gradient descent computes the gradient of the entire dataset to update parameters. It is computationally expensive but can provide a precise update direction. Example, updating model parameters based on the gradients calculated from the entire training dataset. Learning rate. Explanation. The learning rate is a hyperparameter that controls the size of the steps taken during optimization. It influences the convergence speed and stability of the algorithm. Example, a higher learning rate results in larger parameter updates, while a lower learning rate leads to smaller, more cautious updates. Momentum. Explanation. Momentum is a modification to gradient descent that adds a fraction of the previous update to the current update. It helps to accelerate convergence through smoother optimization paths. Example, a ball rolling downhill gains momentum, carrying it through local minima. ADAM, adaptive moment estimation. Explanation. ADAM is an optimization algorithm that combines the ideas of momentum and adaptive learning rates. It maintains per parameter learning rates and adapts them during training. Example, ADAM adjusts learning rates for each parameter based on past gradients and squared gradients. RMSPROP, root mean square propagation. Explanation. RMSPROP is an optimization algorithm that adjusts learning rates for each parameter based on the root mean square of past gradients. It helps handle sparse gradients. Example, RMSPROP adapts learning rates individually for each parameter. Newton's method. Explanation. Newton's method is an iterative optimization algorithm that uses second-order derivatives to find the minimum of a function. It converges quickly but can be computationally expensive. Example, solving equations or optimizing functions using the second derivative information. Conjugate gradient. Explanation. Conjugate gradient is an iterative optimization algorithm used for unconstrained optimization problems. It avoids redundant computation by maintaining conjugate search directions. Example, optimizing quadratic functions or solving linear system using conjugate gradients. Genetic algorithms. Explanation. Genetic algorithms are optimization techniques inspired by the process of natural selection. They involve evolving a population of potential solutions to find the optimal one. Example, evolving a population of potential solutions to find the best parameters for a model. Optimization algorithms are fundamental in solving complex problems, especially in machine learning, where finding the optimal set of parameters is crucial for model performance. The choice of the algorithm and its hyperparameters depends on the nature of the problem and the characteristics of the objective function. Web scraping. Definition. Web scraping is the process of extracting data from websites by using automated techniques to retrieve and parse information. It involves sending HTTP requests to web pages, fetching the HTML content, and then extracting relevant data from the HTML structure. Web scraping is commonly employed for data extraction, content aggregation, and various research purposes. Key concepts. HTML, Hypertext Markup Language. Explanation. HTML is the standard markup language used to create web pages. Web scraping involves parsing HTML to extract data elements such as text, links, and images. Example: in HTML, a P tag represents a paragraph, and web scraping might involve extracting text within these tags. HTTP requests. Explanation: web scraping starts with sending HTTP requests to a web server to retrieve the HTML content of a web page. This can be done using libraries like requests in Python. Example: using an HTTP GET request to fetch the HTML content of a specific web page. Beautiful Soup. Explanation: Beautiful Soup is a Python library for pulling data out of HTML and XML files. It provides Pythonic idioms for iterating, searching, and modifying the parse tree. Example: parsing HTML content using Beautiful Soup to extract specific tags or attributes. XPath and CSS selectors. Explanation: XPath and CSS selectors are methods for navigating and selecting elements in HTML. They provide a way to target specific elements for extraction. Example: using XPath or CSS selectors to locate and extract data from specific HTML elements. Robots.txt. Explanation: the robots.txt file is a standard used by websites to communicate with web crawlers and scraping bots. It specifies which areas of the site are off limits for crawling. Example: checking the robots.txt file to ensure compliance with a website's scraping policies. Scrapy. Explanation: Scrapy is an open source web crawling framework for Python. It provides tools and libraries for creating efficient and scalable web scrapers. Example: building a web scraper using Scrapy to crawl and extract data from multiple pages. User agent. Explanation: the user agent is an HTTP header that identifies the client making the request. Some websites may block requests from certain user agents to prevent scraping. Example: setting a customer user agent in the HTTP request to mimic a web browser. Data cleaning. Explanation: web scraped data often requires cleaning and reprocessing to remove irrelevant information, handle missing values, and format the data for analysis. Example: removing HTML tags, handling duplicate entries, or converting date formats in the scraped data. Dynamic content. Explanation: some websites load content dynamically using JavaScript. Web scraping tools may need to simulate the browser's behavior to fetch and extract dynamically loaded content. Example: using headless browsers or tools like Selenium to scrape data from pages with dynamic content. APIs versus web scraping. Explanation: while web scraping extracts data directly from HTML, APIs, application programming interfaces, provide a structured way to access data from web servers. APIs are often preferred for data retrieval when available. Example: accessing weather data through a weather API instead of scraping it from a weather website. Ethical considerations. Explanation: web scraping raises ethical concerns, and it's important to respect website terms of service, avoid overloading servers, and prioritize data privacy. Example: adhering to rate limits specified by a website and avoiding scraping personal or sensitive information. Legal implications. Explanation: legal considerations in web scraping include compliance with copyright laws, terms or service, and respecting the intellectual property of websites. Example: reviewing and understanding the legal terms and conditions of a website before scraping its content. Web scraping is a powerful tool for extracting data from the web, but it should be performed responsibly and ethically. It's essential to be aware of legal and ethical considerations, respect website policies, and use web scraping for legitimate and non-intrusive purposes. Geospatial data analysis definition. Geospatial data analysis involves the examination and interpretation of data that is associated with a specific location in the Earth's surface. It combines geographic information system (GIS) techniques, statistical methods, and visualization tools to gain insights into spatial patterns, relationships, and trends. Geospatial data analysis is widely used in fields such as urban planning, environmental science, agriculture, epidemiology, and more. Key concepts: Geographic Information System (GIS). Explanation: GIS is a system designed to capture, store, analyze, manage, and present spatial or geographic data. It provides tools for mapping and analyzing spatial relationships. Example: creating a map that displays the distribution of population density across different regions. Spatial data types. Explanation: spatial data can be categorized into vector and raster types. Vector data represent points, lines, and polygons, while raster data are grids of cells with values. Example: vector data might include the boundaries of cities, while raster data could represent land cover classifications. Coordinate systems. Explanation: coordinate systems define how geographic locations are represented on a two-dimensional surface. Common systems include latitude and longitude, UTM Universal Transverse Marketer, and others. Example: using latitude and longitude to specify the location of a point to the Earth's surface. Geocoding and reverse geocoding. Explanation: geocoding is the process of converting addresses into geographic coordinates. Reverse geocoding is the opposite, converting coordinates into addresses. Example: converting the address 1600 Amphitheater Parkway, Mountain View, CA into its corresponding latitude and longitude. Spatial analysis. Explanation: spatial analysis involves examining, interpreting, and modeling spatial data to understand patterns and relationships. Techniques include buffering, overlay analysis, and spatial statistics. Example: analyzing the proximity of schools to parks and identifying areas with a lack of educational facilities. Buffering. Explanation: buffering involves creating a zone around a geographic feature, typically measured in distance units. It is useful for analyzing proximity relationships. Example: creating a buffer zone of 2 kilometers around a river to assess areas at risk of flooding. Overlay analysis. Explanation: overlay analysis combines multiple layers of spatial data to identify areas where features coincide or intersect. It helps reveal relationships between different geographic elements. Example: overlaying layers of land use and transportation to identify areas suitable for residential development. Spatial statistics. Explanation: spatial statistics involve applying statistical techniques to spatial data to analyze patterns and distributions. It includes methods like Moran's I and Grace's C. Example: using spatial autocorrelation to assess whether the distribution of a particular attribute is clustered, dispersed, or random. Remote sensing. Explanation: remote sensing involves collecting information about the Earth's surface from a distance, often using satellite or aerial imagery. It provides valuable data for monitoring environmental changes. Example: using satellite imagery to monitor deforestation or track changes in land cover over time. GPS, Global Positioning System. Explanation: GPS is a satellite-based navigation system that enables precise location tracking on Earth. It is widely used for mapping, navigation, and geospatial data collection. Example, using a GPS device to record the coordinates of trees location in a forest. Web mapping. Explanation. Web mapping involves creating interactive maps that can be accessed and explored online. It enhances data visualization and sharing. Example, developing a web map that displays real-time traffic conditions or allows users to explore historical earthquake data. Spatial data visualization. Explanation. Visualization is a crucial aspect of geospatial data analysis. It includes creating maps, charts, and graphs to convey information about spatial patterns and trends. Example, using a choropleth map to depict regional variations in average temperature. Geospatial data analysis is a multidisciplinary field that integrates geography, cartography, statistics, and computer science. It empowers researchers, planners, and decision makers to make informed choices by leveraging the spatial dimension of data. Causal inference. Definition. Causal inference is the process of determining the cause and effect relationship between variables or events based on observed data. It goes beyond correlation by attempting to establish that changes in one variable directly influence changes in another. Causal inference is crucial in various fields, including epidemiology, economics, social science, and public policy. Key concepts: correlation versus causation. Explanation. Correlation indicates a statistical association between two variables, but it does not imply causation. Causal inference aims to establish a cause and effect relationship. Example, a correlation may exist between ice cream sales and browning incidents, but that does not mean buying ice cream causes brownings. Randomized controlled trials, RCTS. Explanation. RCTS are experiments where participants are randomly assigned to treatment or control groups. They are considered a gold standard for establishing causation in scientific studies. Example, conducting an RCT to evaluate the effectiveness of a new drug by randomly assigning participants to receive either the drug or a placebo. Observational studies. Explanation. Observational studies observe subjects in their natural environment without intervention. Causal inference from observational studies requires careful statistical methods to control for confounding variables. Example, studying the impact of smoking on health by observing a group of smokers and non-smokers over time. Confounding variables. Explanation. Confounding variables are external factors that may affect the observed relationship between the independent and dependent variables. Controlling for confounding is essential in causal inference. Example, in a study on the relationship between coffee consumption and heart health, age could be a confounding variable. Counterfactual framework. Explanation. The counterfactual framework involves comparing the observed outcome with what would have happened in the absence of the treatment or intervention. It helps define causal effects. Example, assessing the impact of an educational intervention by comparing the outcomes of students who received it with what would have happened if they had not. Propensity score matching. Explanation. Propensity score matching is a statistical technique used to balance observed covariates between treatment and control groups in observational studies. It helps reduce selection bias. Example, matching individuals with similar propensity scores in a study comparing the effects of two different medical treatments. Instrumental variables. Explanation. Instrumental variables are used in observational studies to address endogeneity issues. They act as proxies that are correlated with the treatment but not directly related to the outcome. Example, using a natural experiment like changes in policy as an instrumental variable to study the impact of education on income. Heterogeneity of treatment effects. Explanation. Heterogeneity refers to variations in treatment effects across different subgroups. Causal inference should consider how the treatment effect varies among individuals or groups. Example, investigating whether the effectiveness of a new teaching method varies based on students' prior knowledge level. Mediation analysis. Explanation. Mediation analysis examines the mechanism through which a treatment or intervention affects an outcome. It explores intermediate variables that mediate the causal pathway. Example, understanding how a specific drug affects health outcomes by examining changes in biomarkers or physiological indicators. Causal diagrams. DAGS. Explanation. DAGS are graphical representations of causal relationships among variables. They help depict the causal structure of a problem and guide the identification of causal effects. Example, using a DAG to illustrate the causal relationships between education, income, and health in a study. Potential outcomes framework. Explanation. The potential outcome framework views causal effects in terms of potential outcomes under different treatment conditions. It helps define causation in a more formal way. Example, considering the potential health outcomes for an individual under both receiving and not receiving a specific medical treatment. Causation and policy implications. Explanation. Establishing causal relationships is essential for informing effective policies and interventions. Understanding causation helps policymakers make evidence-based decisions. Example, using causal inference to assess the impact of a social program on poverty reduction and inform future policy decisions. Causal inference is a complex and evolving field that requires a combination of statistical methods, study design considerations, and a deep understanding of the specific context in which causal relationships are being examined. It plays a crucial role in advancing scientific knowledge and informing decision in various disciplines. Robustness and generalization. Definition. Robustness in the context of machine learning refers to the ability of a model to maintain performance and make accurate predictions under different conditions, including variations in the input data, changes in the distribution of data, or the presence of noisy or perturbed inputs. A robust model is less sensitive to fluctuations and uncertainties, and it generalizes well to diverse scenarios. Key concepts. Noise robustness. Explanation. Noise in the data refers to random variations or errors that may be present. A robust model can handle noise without significantly impacting its performance. Example, a speech recognition system that can accurately transcribe spoken words even in the presence of background noise. Adversarial robustness. Explanation. Adversarial examples are carefully crafted inputs designed to deceive a model. An adversarially robust model is resistant to these manipulations. Example, a computer vision model that correctly classifies images even when subtle changes are made to the pixels to mislead the model. Outlier robustness. Explanation. Outliers are data points that deviate significantly from the rest. A robust model can provide accurate predictions even when presented with outliers. Example, a fraud detection system that identifies unusual transactions as potential fraud without being overly influenced by legitimate but rare transactions. Distributional robustness. Explanation. A model is distributionally robust if it performs well across different distributions of data, not just the distribution it was trained on. Example, a weather prediction model trained on data from one region that accurately predicts weather patterns in a different region. Parameter robustness. Explanation. Robustness in model parameters refers to the stability of a model's performance when there are variations in the hyperparameters or training settings. Example, a neural network that performs well with different learning rates or architectural configurations. Input perturbation robustness. Explanation. This involves evaluating how well a model performs when the input data is intentionally perturbed or modified. Example, a machine learning model for image recognition that remains accurate even when the input images are slightly distorted. Model architecture robustness. Explanation. The architecture of a robust model is designed to withstand variations and uncertainties in the data. It may involve incorporating features like dropout or regularization. Example, a deep learning model for image classification that includes dropout layers to improve robustness. Generalization. Definition. Generalization in machine learning refers to the ability of a model to perform well on new, unseen data that was not part of the training set. A model that generalizes effectively can make accurate predictions and diverse inputs, demonstrating its capacity to learn and apply patterns rather than memorizing the training data. Key concepts: overfitting and underfitting. Explanation. Overfitting occurs when a model performs well on the training data but poorly on new data, while underfitting occurs when a model is too simple to capture the underlying patterns. Example, an overfit model memorizes noise in the training data, while an underfit model fails to capture the true relationships. Cross-validation. Explanation. Cross-validation is a technique used to assess a model's generalization performance by splitting the data into multiple subsets for training and testing. Example, k-fold cross-validation involves dividing the data into k subsets, training the model on k1 subsets, and testing on the remaining subset, repeating this process k times. Holdout validation. Explanation. Holdout validation involves splitting the data into training and validation sets, where the validation set is used to evaluate the model's performance during training. Example, training a model on 80% of the data and validating its performance on the remaining 20%. Transfer learning. Explanation. Transfer learning leverages knowledge gained from training on one task and applies it to a different but related task. It enhances generalization to new tasks. Example, using a pre-trained image classification model for feature extraction and fine-tuning it on a specific image recognition task. Data augmentation. Explanation. Data augmentation involves creating new training samples by applying random transformations to existing data. It helps the model generalize better by exposing it to diverse variations. Example, rotating, flipping, or zooming images to create additional training examples for an image classification model. Feature engineering. Explanation. Feature engineering involves selecting or transforming input features to enhance a model's ability to generalize to new data. Example, extracting relevant features or creating new ones that capture important patterns in the data. Ensemble methods. Explanation. Ensemble methods combine predictions from multiple models to improve overall performance and generalization. Example, building an ensemble of Decision trees such as a random forest to enhance predictive accuracy. Regularization. Explanation. Regularization techniques such as L1 or L2. Regularization penalizes overly complex models, encouraging them to generalize better. Example, adding a penalty term to the loss function that discourages large weights in a linear regression model. Robustness and generalization are intertwined concepts in machine learning. A robust model is often more likely to generalize well, as it can adapt to different conditions and variations in the data. Techniques that promote generalization contribute to the overall robustness of a machine learning system. Interdisciplinary applications definition. Interdisciplinary applications in the context of machine learning refer to the integration and application of machine learning techniques across multiple domains or disciplines. Machine learning's versatility allows it to be employed in diverse fields, leading to innovations and advancements that bridge traditional disciplinary boundaries. Key concepts: healthcare. Explanation. Machine learning is applied in healthcare for tasks such as disease diagnosis, personalized treatment plans, predicting patient outcomes, and drug discovery. Example, using machine learning algorithms to analyze medical imaging data for early detection of diseases like cancer. Finance. Explanation. In finance, machine learning is used for fraud detection, algorithmic trading, credit scoring, and risk management. Example, developing predictive models to assess the creditworthiness of individuals based on various financial indicators. Biotechnology. Explanation. Machine learning is utilized in genomics, proteomics, and drug discovery to analyze biological data and identify patterns. Example, predicting protein structures or identifying potential drug candidates through machine learning algorithms. Environmental science. Explanation. Machine learning aids in environmental monitoring, climate modeling, and analyzing ecological data for conservation efforts. Example, predicting deforestation patterns or monitoring changes in biodiversity using machine learning models. Marketing and e-commerce. Explanation. Machine learning is employed in recommendation systems, customer segmentation, and personalized marketing campaigns. Example, developing algorithms to recommend products based on user preferences and behavior. Education. Explanation. In education, machine learning is used for adaptive learning platforms, student performance prediction, and personalized learning experiences. Example, creating systems that adapt the difficulty of educational content based on a student's learning progress. Agriculture. Explanation. Machine learning is applied in precision agriculture for crop monitoring, yield prediction, and disease detection. Example, using satellite imagery and machine learning algorithms to predict crop yield and optimize farming practices. Manufacturing and industry. Explanation. Machine learning is utilized for predictive maintenance, quality control, and optimizing production processes in manufacturing. Example, implementing algorithms to predict equipment failures and schedule maintenance in a manufacturing plant. Social sciences. Explanation. Machine learning contributes to social sciences by analyzing social data, predicting social trends, and understanding human behavior. Example, analyzing social media data to study public sentiment or predict social and political trends. Transportation. Explanation. In transportation, machine learning is used for traffic prediction, route optimization, and autonomous vehicle development. Example, developing machine learning models to predict traffic patterns and optimize transportation routes in a city. Energy. Explanation. Machine learning is applied in energy production, consumption prediction, and optimizing energy efficiency. Example, using machine learning algorithms to predict electricity demand and optimize the operation of power grids. Humanitarian aid. Explanation. Machine learning is employed in disaster response, resource allocation, and analyzing data for humanitarian efforts. Example, using satellite imagery and machine learning to assess the impact of natural disasters and plan effective relief efforts. Urban planning explanation. Machine learning is used in urban planning for analyzing population trends, predicting urban growth, and optimizing city infrastructure. Example, predicting future housing demands based on population growth and demographic changes. Criminal justice explanation. Machine learning is applied in criminal justice for predictive policing, crime pattern analysis, and recidivism prediction. Example, developing algorithms to predict areas with a higher likelihood of criminal activity to allocate police resources effectively. Entertainment and gaming explanation. Machine learning is used in entertainment for content recommendation, user engagement, analysis, and developing artificial intelligence characters in games. Example, personalizing movie recommendations on streaming platforms based on user viewing history. Interdisciplinary applications of machine learning showcase its adaptability and impact across a wide range of fields, leading to advancements and solutions to complex problems in various domains. Collaboration between machine learning experts and domain specialists is crucial for successful interdisciplinary applications. Continuous learning definition. Continuous learning in the context of machine learning refers to the ongoing process of acquiring and updating knowledge, skills, and models to adapt a new data, emerging trends, and evolving technologies. It emphasizes the dynamic nature of machine learning systems, acknowledging that models need to evolve over time to maintain relevance and effectiveness. Adaptive models explanation. Continuous learning involves developing models that can adapt to changes in the data distribution, allowing them to remain effective as new information becomes available. Example, an autonomous vehicle's perception model continuously updates based on real-time sensor inputs and learns from new driving scenarios. Incremental training explanation. Rather than retraining models from scratch, continuous learning involves incrementally updating models with new data to incorporate the latest information. Example, training a natural language processing model to understand and generate new language expressions as they emerge over time. Concept drift management explanation. Concept drift occurs when the statistical properties of the data change. Continuous learning systems actively monitor and adapt to concept drift to maintain accuracy. Example, an e-commerce recommendation system adjusting its recommendations as user preferences evolve. Online learning explanation. Online learning involves updating models in real time as new data arrives, allowing systems to adapt and improve continuously without the need for batch retraining. Example, a spam filter learning to identify new types of spam emails as they appear without waiting for period updates. Transfer learning explanation. Continuous learning often leverages transfer learning when knowledge gained from one task is applied to accelerate learning on a related task. Example, using a pre-trained image recognition model as a starting point for training a model on a specific set of images. Feedback loops explanation. Systems in continuous learning often include feedback loops that enable them to learn from the outcomes of their prediction and adjust their models accordingly. Example, an online customer service chatbot learning from user interactions and refining responses based on feedback.